Welcome to UVU CS3060 Lecture 2.4, where we talk about how some operating systems are structured, as well as give some examples of those structures. So let's begin. So again, remember that a general purpose operating system is usually one very large program, the operating system kernel, along with several small system programs. We're going to talk mostly about the operating system kernel in this particular lecture. We're going to talk about simple structures such as MS-DOS, one of the originals, more complex, such as Linux and other Unix-based operating systems, layered, and then we'll also talk a little bit about the microkernel approach, which is what macOS uses in certain ways. Now, the original MS-DOS, this was the first operating system that was released for IBM personal computers, was really just simply the smallest program they can write to give the functionality that was necessary. If we talk about policies and mechanisms, the policy here was just give them what they need, and the mechanism was a small program. It wasn't divided into modules at all. There would be a system program that would usually stay in memory the entire time. It was usually very small. It relied on MS-DOS device drivers, which were usually just separate programs themselves, to get to your actual devices. And the application program could interact with the operating system, or it could actually interact with the devices directly, which was frequently the case. And there was very little separation between user space and kernel space. So let's move into the world of the Unix operating system. So the original Unix operating system had very limited structuring. Really, there were system programs in the kernel, and you still see that a lot. But the kernel consisted of everything below the system call interface, as we've talked about, and provided things such as file systems, CPU scheduling, memory management, and other operating system functions. And usually it did this all in one layer, but it prevented the actual user space or system programs from doing anything that the kernel did, owing to the separation between user space and kernel space. So a traditional Unix system was layered usually like this. You had your user that would use things such as shells and commands to get things done. At which point the operating system kernel would handle many of the services that you see here. The kernel would then work with the hardware using device drivers and such to operate hardware controllers. Now, we've already been through most of this. This is actually going to be the model we will follow as we go through this class. Now, in most cases, an operating system is maintained as a layered approach, and we try to keep different functionality within particular layers. So at the very base is your hardware layer. This is the core. This is the system that's being run. Layer 1 is usually device drivers and things that work directly with device controllers. Other layers may include things like file system drivers or network drivers or protocol drivers. And usually whenever you get far enough out, you'll have the user interface. And that user interface is a layer to itself. Now, what layer are each of these drivers in? Well, it usually, or each of these functions in. It usually depends on what the function needs to access in ways of operating system functionality. So what we've been demonstrating with this particular kernel, let's go back a couple of slides. We consider where we have one big operating system kernel that does all the functionality here. We call this a monolithic kernel. A monolithic kernel just simply takes up all this space, does all the functionality. It's usually maintained by one vendor. In the case of Linux, the entire source code for the kernel is available. It is millions of lines long, and it is very difficult to manage. But one of the biggest problems with the monolithic kernel is if something goes wrong here, the whole kernel crashes. This is the same thing with Windows. The Windows operating system has a monolithic kernel. This is one of the reasons why when your operating system crashes, you get that blue screen of death. That famous blue screen of death is just simply indicating the operating system kernel can no longer function and must halt. Another type or design of kernel is called the microkernel. Now, a microkernel, what it does is it tries to move as much functionality as it can from the kernel back into user space. So the Mac OS X kernel is considered a microkernel. There are things it does within its main kernel level system that it has to do, but it tries to push as much as it can back into the user space. So for example, we have here when file system operations need to be taken care of, those file system operations can be managed within the user space and then control whenever a device needs to be contacted. Then it can go into the microkernel to perform microkernel operations. All of this is done between modules using message passing. Now, you're familiar with function calls. You're familiar that you can make a function call and send parameters. And at least within the machine code, all the function call is doing is jumping to a new instruction. It's changing the program counter. Message passing is significantly different in that it will take a particular information that needs to be exchanged between modules, and it will move that through the kernel and then to the appropriate module. Here's a diagram of a microkernel system. Here's our application program that may need to perform some sort of file operation. Let's say it's trying to perform an open. What it will do is it will form a message, and it will pass that message through the microkernel. The microkernel will figure out that message needs to go to this file system. The file system will do what operations it needs. Generally, one of those operations is to save something to it or read something from a device. It will create a message, send it through the microkernel into the device driver. The device driver at that point will access the device directly. Once that information is obtained, that message will be returned back to the file system. The file system driver will take that information and send it back to the application program, at which point the program can continue running. Really, in a microkernel system, you almost always have three things. You have some form of inter-process communication, which allows for this message passing. You have some form of memory management, which allows for the allocation of memory. And finally, you have some way of scheduling these processes in the user mode onto a CPU. All of this is necessary to accomplish the functionality. Now, you probably are going to wonder, why don't we do this? Because really, if a file system crashes, let's say this file system goes down, the rest of the system all the CPU scheduling and memory management and such won't go down. In fact, a good microkernel will restart the file system and try again. This is slow. All this message passing, going from file system to device driver, having the device driver go to the hardware through the kernel, having the device driver respond back to the file system, this is not considered efficient operation, but it is safe. So there's a trade-off here. Microkernel systems have gotten better, and there are quite a few microkernel systems that try to lower some operations back into the kernel for efficiency's sake. Now, a lot of operating systems will use what are called modules to get work done. This is true for both monolithic kernels as well as microkernel design. Now, when it comes to using modules, what happens is a kernel will start up with limited functionality. As functionality is needed, a kernel module will be loaded, or a loadable kernel module will be put into memory, and then the kernel will send operations to that. It's kind of an object-oriented approach to working with operating system functionality. We try to keep, so with modules, you try to keep separation between core components. You have each module talk to each other using known interfaces, very similar to system calls. And you only load these modules as they're needed within the kernel. And the Linux kernel you can actually choose whether to build your entire kernel with all the drivers you need into one big kernel, or to use loadable modules. Most Linux distributions are modular in design. You don't use every single device driver that comes with Linux. And trust me, there are many, many device drivers in Linux. You only load what you need. And you can see the modular approach here of this diagram for the Solaris kernel, where there are various file systems, executable formats, devices and bus drivers. You have different ways of scheduling processes. All of these are modular to the Solaris kernel. Solaris kernel itself doesn't do much more than load modules and then have the modules communicate to each other. You can't consider this a microkernel, though, because all of these modules are loaded and used while the CPU, while the processor is running in the privileged mode. And so while it can be loaded at a separate time, it still runs in kernel mode as if it were a single program. And if a file system crashed in this particular case, the entire operating system kernel would go down. So while this is convenient for keeping functionality in different modules, it is still not the safest, not as safe as microkernel design. Frankly, a lot of systems are fairly hybrid in this model. There's really no one pure microkernel or one pure monolithic kernel. The Linux kernel does a lot of things that are considered monolithic, and it has modular aspects. But there are also microkernel functionalities, such as the user file system, or Fuse. Linux will actually allow you to create your own file systems that other programs can use through the kernel, through a kernel interface. So there's a strange hybrid going on here. OS X actually has several things built into the kernel. You have the when it comes to the Mac OS kernel, you actually have BSD, which is an open source variant operating system. And there are various kernel extensions and an I/O kit, but you do have application environments and servers, such as the Cocoa environment, which is a development interface, and a Java environment. All of these have to work through the kernel environment, but there is a lot of functionality within the mock kernel that goes above and beyond just a standard operating system kernel. The iOS is actually very similar to Mac OS X. It uses a lot of the same code, in fact. It does not run OS X applications natively. It has a different interface on how these things work. There's Cocoa Touch. It used to be Objective-C. It is actually moved to Swift. There are various media services that are available in the iOS kernel. And then finally, we have some core services. These core services are things that apps normally use, such as cloud computing interface and database interfaces and such. And then finally, we have the core OS. All of this is part of iOS and part of the iPhone interface. Android, on the other hand, is very similar stack-wise to the iOS, but it is based on the Linux kernel, and highly modified Linux kernel. It provides some process memory and device driver management, but it also provides enhanced power management. When it comes to mobile devices, you want your battery to last a long time, and so the actual operating system kernel has built-in power management features to minimize the amount of CPU being used. Lots of runtime environment functionality is included that is very much Java-based. You have, in effect, most apps are Java class files and that are translated to be executables that run on this Dalvik VM. You have various libraries and frameworks such as WebKit and SQLite, just like you would see in the iOS. Now, like we've said before, all operating systems will be based on the hardware, and iOS and Android is very specialized, and so the operating system is very specialized. And here's a diagram of the Android architecture, the libraries that are usually available to all the different apps that are running, and then you have the Android runtime, which ends up being the actual operating system. This is the end of the UVU CS3060 Lecture 2.4, where we discuss operating system examples.